Welcome back, Algebra Express. We are in Rockswold 4.6. So we're going to continue talking about rational functions and models here. So in the previous sections, we were talking about rational expressions. So now we're going to turn them into basically functions and talk a little bit about what they look like graphically. So the first example, they give you a word problem, rational functions in our lives. Average cost per unit. Suppose that the cost of producing X bicycles is given by the function c of x equals 32,000 plus 75x. Find a function a of x that computes the average cost per bicycle. Okay, so they're giving us a word problem, but if I didn't give you a bunch of symbols, you could probably tell me you're going to sum up all the prices of the bikes, right? And then divide by what? The number of bikes. And that would give you an average cost per bicycle, just sort of like if you want to average grade it, just sort of like if you want to average anything, right? You're going to sum them all up. You're going to divide by the total number. So if we want to do that, I'm going to do it in function notation now. So one way I could write this is that I want the cost of all the bicycles. So that is my c of x function. Now I want to divide by the number of bicycles. And so the number of bicycles is just the variable x. So we can put c of x over x, or we can say something like a of x is, we know what c of x is 3,200 plus 75x over x. Okay. The next one, we have a distant rate time problem. The good thing is you probably won't have to make the table for this thing. Find a function t that takes as input the average rate r and calculates the time required to travel a fixed distance of 300 miles. Okay, so if you remember distance, rate, time, we said something like distance is equal to rate times time previously. And if you think about your maybe like a unit analysis, like our distance might be measured in miles. Our rate might be in something like miles per hour. Our time might be in something like hours. So if we just look at the units on this thing, there's a thing called unit analysis, and it works very much like the previous sections when we were doing simplification, right? You can look here, I do miles times hours. By hours, I should get something in miles, which is what I'm getting, right? So these units do match up. Typically, when you're dividing by something, right, miles per hour, the next variable is going to have to be like hours, right? It's going to have to be the thing you're dividing by so that your units simplify. But we want a relationship. And they basically say a function t. So that means we're solving for t. So maybe I should take my variables and make my t capital, my d lowercase maybe. That's the thing I'm going to be solving for. I want a t of r function. So how does t relate to my distance and my rate? By r. It would be something that looks like d over r. So I can look at this as a function notation. T of r over r. And here we know our distance. It is a fixed distance of 300. That will give us what they're talking about. And if we're looking at this thing, 300 over my rate. So if I do 300 and I divide it by 0.9, let me double check it. Does it give you exactly that? They might be a bit off with these first ones. I think these are more accurate. So I'm not sure what they're doing in their notes. Maybe they're trying, well, it doesn't say this is coming from an anecdotal sort of experiment. So I don't know. I don't know what they're doing. But this is your function. These were accurate when I checked them. These were less accurate. They were close. Okay. Definition of a rational function. So if we have a rational function, it looks like p of x over q of x, where they are both polynomials. So this is the same thing as a rational expression. Determine whether the function is rational, if so, find the domain. Okay, so we talked briefly about the domain restrictions, and the domain restrictions are coming from the denominator. So there's a number our denominator can never be, and that thing is 0. We can never divide by 0. Don't divide by 0. It makes the universe. And so first we want to determine whether this is a rational function. Is 2 a polynomial? 2 is absolutely a polynomial. Constants are polynomials. X minus 1 is definitely a polynomial. It's x to the first power. So I guess I need the word yes. And I want to find my domain, or I want to find my domain restriction. So in order to find that, I want to know what makes x minus 1 equal to 0. If I solve that, I figure out it is x equals 1. So this is the thing that it cannot be. So this is my domain restriction. Okay. Now we want to determine if this thing is a rational function. So we see square root of x over x squared plus 2. X squared plus 2 is a polynomial. Square root of x. We talked briefly about this, but we can think about this as a fractional power, like x to the 1/2. And we talked about this before. We wanted to define polynomials, but this is actually not a polynomial, so this is not a rational function. We could still look at domain restrictions, and if we wanted to do that, I'd be asking myself, where is x squared plus 2 equal to 0? And so I'm looking at this x squared plus 2 equals 0. I want to know my domain restrictions, and I'm talking about within the real numbers. We're not using the complex. We're talking about within the real numbers. And if we do that, you might realize you're getting for your solution. You're doing the square root principle. You're going to get imaginary things, is what I'm trying to get at. And so there are no domain restrictions here. All your restrictions are imaginary. We're just talking about being within the real numbers. So if the only restrictions are imaginary, there are no domain restrictions. Or you could say the domain, right, or is all real numbers. Okay, so we're looking at this thing. We see x squared minus 1 on top, 4x squared minus 4x on bottom. Is this a polynomial? Yes, it is. Is this a polynomial? Yes, it is. Is this a rational function? Yes. Okay. So we want the domain restrictions. So we want to know where 4x squared minus 4x is equal to 0. Okay, so if I want to solve this, I need to factor this thing. So if I factor this thing, I believe I can pull out a 4x, and that's going to leave me with what? X minus 1, and this is equal to 0. So I'm solving this thing. So I do have one solution. Don't forget this solution, which tells me x equals 0 or x equals positive 1. So again, I'm finding my domain restrictions. If I want my domain, it's x cannot be 0, x cannot be 1. If you go and try to plug these back into this equation, you're going to get a 0 on the bottom, right? Okay, so with that said, the bottom factor to 4x and x minus 1. To remind you, this is like x plus 1, x minus 1. So you might notice one of these things does simplify out. So this does simplify out, but it is still a domain restriction, right? We can only simplify this out if it is a big fancy 1. And so x equals 1 is still a domain restriction, because if this was 0 over 0, 0 over 0 is actually indeterminate, right? We can't do something like that and simplify that out. You'd end up with some sort of problem like that. We've got to make sure these are numbers other than 0, right? And so x cannot be 1 because of this thing. So with this thing, I'm looking at this and I'm thinking, is this a polynomial? Is this a rational function? So I don't see anything on the bottom. I'm thinking it's got to be a polynomial over polynomial. Well, guess what? I can always put 1, and we can think of this as a rational function. And if we think of this as a rational function, sure, I guess so. What is my domain restriction? So 1 cannot be what? 0? Okay, I don't think 1 is ever going to be 0. I believe my domain is all the real numbers. Okay. Here, they just want you to recognize what an asymptote looks like. And so if we wanted to write the equation, y minus 3. So the equation of this asymptote would be like something like y equals minus 3. And so this is going horizontally. And so what does a horizontal asymptote look like graphically? Well, as the graph goes off to what? Infinity, this thing is going to get infinitesimally close, but not touch it, right? It could hit somewhere in the middle, right? This one does. But as it goes off to infinity, this thing is going to get infinitesimally close. So this is coming from the top and getting infinitesimally close from the top, right? It's getting smaller. This one is coming from the bottom and then it's getting infinitesimally close to it, but it never touches it, right? It doesn't touch it, but it gets really, really close. That would be a horizontal asymptote. So what does a vertical asymptote look like? This looks like x equals 1, 2, I believe. X equals 2 is the equation of this line. So as the line approaches a vertical asymptote, it either shoots off to infinity or it could shoot off to negative infinity. So I know it's going up here and up here, but I could have a line and it could be going down. It shoots off and it never hits it. So an asymptote, one of the key features is that they never cross, right? The line never crosses the asymptote. It gets infinitesimally close, but it never crosses. Okay, so if the line never crosses this, what does that mean about the domain of our line? So we've been finding domain restrictions. These are going to be domain restrictions, right? Our line never crosses it, means it's never going to hit this value, which means this is a restriction on our domain. It can never be included in our domain, right? Okay, so if we want to find vertical asymptotes, if we want to find the asymptotes, we do have to simplify it first. Okay. So if we're looking at this, this looks like 2 over x minus 1. Are these the exact same ones from the previous page? Oh, darn. Yeah, okay, so this one is the same one. I think this one might be a new one, but that is definitely the same one. Okay. If we want to find the vertical asymptote, we got to make sure it's fully simplified. If we look at 2 over x minus 1, I don't think there's any common factors I can take out. So my vertical asymptote here is going to be the thing that makes this 0. It's going to be my domain restriction. Find the zeros of the denominator. So we simplify, then we find the zeros. So this is x equals 1 is my vertical asymptote. Okay, and just to re-emphasize, let's go to Desmos over here. X equals 1 is this line happening right here. And if you notice my graph, it shoots off to infinity in this direction. It shoots off to negative infinity in that direction. Now we have something like 4x cubed minus 1 over x squared plus 2. So if I want to know where my vertical asymptotes are, I fully simplify this thing. So x squared plus 2 does not factor. That's like a sum of squares. It doesn't factor evenly, right? It's going to give us, and we solve this around x squared plus 2 equals 0. If we want to solve this, we have to subtract the 2, and that's going to end up giving us things that are imaginary. I was about to say irrational. That's imaginary. Okay. There are i's in it. Pluck out the So what does that mean about its asymptotes? Well, I'm glad you asked. So let's look over here at Desmos again. This is what this graph looks like. So you might notice it doesn't have any asymptotes. And then the last graph. So we've already factored this thing. X plus 1, x minus 1, and x minus 1. And I talked about, hey, this is simplified away. And so if we want to find our asymptotes, we only want where the 4x is equal to 0, which is where my x is equal to 0. So this is my vertical asymptote on this thing. So this one had a just to recap, this one had a vertical asymptote. This implied there were no asymptotes, right? No vertical. Because we got imaginary solutions. We're talking about the real numbers when we graph things. There's no vertical asymptotes on there. So this one has a vertical asymptote. x equals 0. But we also know it has something weird happening at x equals 1. So what's happening at x equals 1? Because we know it's a domain restriction, but it's not a vertical asymptote. So let's go back, look at this thing. Where is that? Share my Desmos over here. Let's plot this up here. X equals 0. So if I want to do that, that's my axis here. My y-axis, you notice as it gets close to the y-axis, and I could zoom in maybe a little bit. As it gets close to the y-axis, right, it's shooting off to infinity, negative infinity there. But we had something weird happening at where x equals 1. So if I'm coming along here, can I hit it? Come on. Oh, what's happening there? It's undefined. What does that mean? Can I zoom in? Does it show it if I zoom in? So it's like it's there, but as soon as we hit the number 1, oh man, I thought they showed it. Okay, I guess they don't. As soon as we hit the number 1, it becomes undefined. So what we call these things is it's like a hole in the graph, right? So these are called holes. It makes the whole thing if I do it over it. That's how you get it. Where's it at? If I get the 1 undefined, see, it's a empty circle. So it like goes up to there and we put a little empty dot. It's an empty point. These are all solid points. So there's an empty point at 1. Or we call it a hole. There's a hole in the graph. There's a hole in the middle of the graph. There's a hole in the middle of the graph. Okay, so those are vertical asymptotes. So vertical asymptotes, you simplify things. If it comes out, it was a hole. After you simplify it, if it doesn't come out, we solve it for 0, and it is a vertical asymptote. So after you simplify it, you get your asymptotes. Before you simplify it, those things were holes, right? The things that simplify out, we still can't use them, but they're not affecting our graph the same way in asymptote. It's not shooting up to 0. So vertical asymptotes, you just set the denominator equal to 0 when it's simplified. You solve. That I feel like is a little more straightforward than this thing, which are our horizontal asymptotes. And there are 3 different ways. And so basically what we're going to look at when we look for a horizontal asymptote is the degree of the polynomial. So if it is the same degree versus if the numerator has a greater degree versus if the denominator has a larger degree. So there are 3 different ways, right? On top, right? Or they can be the same. I think they give us an example of one of each. So we want to look at the degree of the polynomial. So this is an x to the first. This is sort of like an x to the 0. Okay, so I want to think about what is happening. So if I think about this function, I'm doing 2, and if I do like 2 over what x, when x is 10, I'm going to get 2 over 9. And as I keep increasing x, so I want to think about what happens as I shoot off to infinity, right? Is what our horizontal asymptotes look like. What happens if I go off to infinity? What happens if I go off to negative infinity? What does my graph look like? Is it leveling out? So 2 over 9, so like I go to 2 over a million, I'm going to get like 2 over 9999, right? What is happening to this number? And I guess I could do like a decimal approximation. This is going to be 0.222 repeating. What was that, 5 nines? This is like point with 4 zeros, I believe, and then 2, 0, 0, 0, 2 or something like that. I think I might be missing another 0 in there. What is happening to this thing? You might notice that 2 is not doing a whole lot. It's this denominator doing all the work, and it is getting really, 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 really large, right? And I want to know what I can say about this thing. I know this thing is going to be positive for one. It's going to be really, really small, but it's never going to hit 0, right? It's still going to be positive. It's not going to quite hit 0, but this is sort of going over like 1 over, and if this thing is shooting off to infinity, right? If I get a really, really large number, right? This is going to 0, basically. That's really horrible mathematization, but I think it maybe gets the point across, right? If I get 1 over or even 2 over a really, really, really large number, right? 1 or 2 is not going to make a big difference. It's this number right down here doing the work. So if your denominator is larger, it's a larger polynomial. This is doing more work, and it's like 1 over a really, really large number. What you're going to end up getting is an asymptote at y equals 0. And again, that's because this is smaller. It's a smaller degree polynomial. This is a larger degree polynomial. Okay, so now we look at this thing. And now we might notice, hopefully notice the degree on a polynomial. This is a degree 3. This is a degree 2. And if they're not written in descending order, you might have to write these in descending order to get your polynomial degree, right? We did that back when we did polynomials. But if we're looking at this thing, you might notice this thing is larger over smaller is the scenario we have here. So this thing is going to be doing more work than this thing. So as we go to larger and larger numbers, like 1,000, right, or 1,000,000, we're going to be multiplying this by 1,000,000 more each time as we get larger. And so for like this one, I was getting you to try to think about like something like 1 over something going to infinity, right? 1 over a really, really large number is really, really close to 0. And so if this is like 1 over infinity, maybe we can think about like this, like it's like this is shooting off to infinity way at a way faster rate than like this sort of thing down here. If that's the case, if we think about things going off to infinity, the graphs going off to infinity on their ends, right? Does something like that have an asymptote if it's going off to infinity? It's not leveling out, it's going off, right? So this is the thing that has no asymptote. And that's because we have something larger over something smaller. So if you think about like 1 over a really large number, that's like it's going off to infinity. If it's a really large number, we can't really say anything about the ends. It's just shooting off to a really large number. It just keeps going up and up, basically, right? And the last sort of scenario we have is that they are the same degree polynomial. So if you have the same degree polynomial, make sure they're written in descending order. We have an x squared and an x squared here is what I'm seeing. I do want to know what my exponent is, or my coefficient here is, sorry. Which, if I don't see it, it's 1. Okay, so this has a horizontal asymptote, and this is the thing that might be a little bit weird, but this has a horizontal asymptote at y equals, and we just take the coefficients on our function, like y equals 1/4. Okay, so maybe back. Let's go back to that function. Let's see what this y equals 1/4. And this is the one where they have the same degree, right? It's the same degree. Top and bottom, it's the same leading degree. So let's go back to Desmos just for a second. Oh, let's do that 2 over x minus 1, right? And this one had a 1 at what y equals 0 is this guy's asymptote. So if we zoom out, we might see as it shoots off to what, infinity, negative infinity, this y equals 0, it's never going to cross that line. Okay. And again, this is if it's a larger degree on bottom, it's like 1 over a really large number, or 1 over going to infinity is going to be really close to 0, but never quite 0. Here we go. Again, we look at this thing, y equals x squared minus 1 over 4, x squared minus 4. If we look at this thing, we got y equals 1 over 4 as our horizontal asymptote. Maybe let's change it to a different color. There we go. And so if I'm looking along here, as it shoots off to infinity, it gets really, really close to this line, but it's never going to cross it. As we go off to this direction, it gets really close, but it's never going to cross it. So that's what this guy's looks like. And remember, it's got what? Horizontal asymptote at x equals 0. So if you have to graph these things, the best thing to do is to start out with these asymptotes. That's kind of why we're finding it. We're looking at graphs. We try to see what asymptotes are, then we're trying to see how to solve them symbolically. And then they'll probably have you graph some of these in a minute. So there are basically three sort of scenarios. We're looking at the powers on the numerator and denominator, and there's basically three sort of scenarios that those could possibly be. And so each of them have a sort of different outcome. So 1 over x. So this is like I was saying, 1 over x. As we go to infinity, if we do 1 over a really small number, it's going to shoot really, really close to 0, but never quite reach it from the positive side. If we start plugging in a really, really large negative number, this thing is going to go towards 0, but from the negative side. And 1 over a really small number, the smaller the number gets as a fraction, it's going to shoot off to infinity, right? So if we plug in a positive number, it's going to shoot off to positive infinity. If we plug in a negative fraction, it's going to keep getting larger and larger in the negative direction. So 1 over x, if you have to plug in some numbers, mess around with this thing. I'm hoping this, like the shape of this thing is making sense. 1 over a large number is really small. 1 over a small number is really large. And if we throw a negative in there, it's going on from the other side. So y equals 1 over x squared. What's the difference between like an x and an x squared? Well, if we square something, it's always going to be positive. So it is a little steeper, but one of the sort of defining features here is that it is all positive, right? It is all on one side of that axis. It is all on the positive side. Now we want to graph things by transformation. Then identify the asymptote from the graph. Okay, so I'm asking myself, what is my parent function on this thing? I don't know why they wouldn't. You don't want to identify the asymptotes from the graph. You want to identify your asymptotes to graph this thing, I think. So that's probably not the best instructions. I would go about it a little differently. But we can pretend like we're getting them from our graph if they really want us to. Okay, so if we want to look at a parent function, this looks like y equals negative 1 over x minus 2 squared. And you're asking yourself, well, are they giving me this one or this one? And the defining thing between this one, it's the first power. This one is a square power. So if we see a square power, they're giving us the square function. So I'm seeing two things happening here. I'm seeing a -2. Let me do it in red, maybe. I'm seeing a -2 and I'm seeing a negative sign. So there are two things that I'm doing. The -2, is that happening to the X quantity or the Y quantity? It's almost directly attached to the X. So this is definitely happening to our X quantity. It is happening reversible, it might think it is. This is moving it to the right too. So we want to move our whole graph to the right too. And this, is it happening on the X or the Y quantity? So I could cover that up. That's about as outside as you're going to get on this thing, right? It's outside of the division bar. It's outside of the square. This is way on the outside. This is going to flip my Y quantities. If I flip my Y quantities, I'm going to flip about X. So I want to take this graph. I want to move it to the right too. So one of the defining features you might have noticed in these things, and I probably should have done them, but this has an asymptote here. Our asymptote at X equals 0. So has a horizontal asymptote at Y equals 0. It is greater in the bottom. It is a larger power in the bottom. We're going to get a horizontal asymptote of Y equals 0. If we set the denominator equal to 0, we're going to get 0. If we set the denominator equal to 0 here, we're going to get 0. If we look at the powers, it is still greater on the bottom. So you might notice these have the same asymptotes at X equals 0 and Y equals 0. And this is really like the sort of feature that I'm really interested in, right? I draw my asymptotes and I draw a little bit of a curved line. This one should go through 1, 1 and negative 1, 1, negative 1, 1, 1 and negative 1, 1. So those are maybe some points I want to capture. But the rest of it is pretty much just going to be like draw a curved line, right? I'm not going to be really specific about how you're drawing this thing. So the first thing I kind of want to start off with is my asymptotes. So if I'm doing this line and I'm moving it to the right too, you might notice my new asymptote is going to be right here along with X equals 2. I'm moving this to the right too. And if I did that, I would have one line going like swoosh and one line going like swoosh, like this and like this. So this is to the right too. But now I want to flip it about the x-axis. So now it's getting flipped down. So instead of up here, it's going to come through down here and down here. This is still my asymptote. I'm not changing this asymptote. And so if I wanted to maybe do the graph before the flip, this is the graph moved to horribly drawn. But this would be my graph moved to the what? The right to curvy. But now I'm flipping it. So this black graph is the final graph that you should be drawing. Something like that. It should look something like that. So it should not cross your asymptote. It should be a little bit curvy, maybe. Kind of hard to draw. So my vertical asymptote, we already talked about it, is now going to be moved to the right. So instead of X equals 0, it's going to be X equals 2. My horizontal asymptote did not change. Y equals. Okay. So now I'm looking along here at the second one. F of x equals 2 minus 1 over x. I might want to rewrite this. If I write this as a minus 1 over x plus 2. That might help me out a little bit. So which one is this? And I hope you get it right away. It's just the 1 over x. There's no square happening here. We're not squaring anything. So I have this thing. I look at it. And I see two things happening here, I believe. Here and here. So I want to know what these two things are doing. So I already have the 1 over x. So this is like I'm taking the function. So this is on the outside of this entire function. This is happening to the y quantities. I believe I'm going to flip about x. And plus 2 is then going to move it up to, that is also happening on the outside to the y quantity. Okay, so now I'm looking along here. I want my 1 over x graph. I want to flip it about the x-axis and then move it up 2. So I have a graph. My 1 over x graph looks something like this. If I flip it about the x, this thing is going to come down here. This thing is going to come up here. That is not going to change. If I flip it, it's not going to change my asymptotes. If I move it up 2, it will change my asymptotes. So now I'm moving this whole thing up 2. It's going to change this asymptote up 2. That is asymptote going up 2. And again, instead of going like this and like this, it's going to go like this and like this because it's flipped. So if I want to go like this and like this, make a little curvy, it doesn't fit my asymptote. Y equals, what am I doing? 2. And x equals 0 are my two asymptotes. And we can do them graphically, sort of like this, graph transformations. If we solve these things symbolically, right? If we solve this for my vertical asymptote, I want to set my denominator equal to 0. I get x minus 2 squared equals 0. X minus 2 equals 0. I get that twice. So x equals 2 is my vertical asymptote. I can get that symbolically. Y equals 0. I know it's a larger degree polynomial on the bottom. Y equals 0 is still going to be my asymptote. I can kind of do the same thing here if I want to do my vertical asymptote here. The only fraction I have here is this 1 over x. So if I find the vertical asymptote of this thing, I'm going to get x equals 0. Now, my horizontal asymptote might be a little trickier. If we wrote this, we probably could get it. If we rewrote this with like denominators, it would probably come up. But there's actually an easier way. If I want to do the vertical asymptote of this is 0, and then I'm adding 2 to it, would give me y equals 2. Or I could do like a common denominator, like I said, right? I could do 2x over x minus 1, I think is what this would be if I combined it. This would also give me the y equals 2 if I made this into a common denominator. So we should be able to do this symbolically as well, right? As graph transformations. And hopefully they match up. And this should be consistent, right? That is one of the things math is known for. All right, so now we want to talk about deer populations and removing smokestack pollutants from a coal plant. We got two word problems. Interpreting asymptotes. Deer population in a state game park 2 months after the introduction of 60 deer is given by this crazy thing. Find the horizontal asymptote. Okay, so we want to find the horizontal asymptote. And it's a little tricky here. This is 20t plus 60. This is 1 plus 0.05t. So before we do this thing, we really want to rewrite that denominator. Put it just in order. So here we go. 20 over. Ooh, I'm giving you too much. So now we're looking at this. I want to do horizontal asymptotes. I'm thinking, is it smaller over larger, larger over smaller, or is it the same power? So if we look along here, we look at t to the first, t to the first. This is the same power. So if it's the same power, the rule is to take the coefficients and divide them. So 20 over 0.05 is giving me 400. And so this is like my y asymptote, my n of t. And so my horizontal asymptote is, you could say, I guess you could say y equals 400. I'm going to go with n of t because that's what my variable is here. And if we look along here, flat line somewhere along there that it's not hitting up there. What does that mean? Deer population in a state game park 2 months after introduction of 60 deer is given by this function. So you put in deer and they populate at a pretty quick rate, and then that rate starts leveling off. Why is that rate leveling off? Well, this is where you're pulling in sort of like your knowledge of the world around you, right? Why would deer not be able to go past a certain population in a certain area? $400 is probably like the max sustainable population, right? Something along those lines, like with limited resources, right? That's what we're talking about here. This is like the environment is not going to sustain any more deer. Okay. So the cost, C, in thousands of dollars of removing P% of smokestack pollutants from a coal plant is given by C of P equals 80P over 100 minus P. Excuse me. Okay. So we talked about like vertical asymptotes, things leveling out is what a vertical asymptote would look like. So this is like a population leveling out or a max sustainable population of an area, right? Now we want to talk about what a vertical asymptote sort of looks like. So we want to find the vertical asymptote. So again, finding the vertical asymptote, how do we do that? We got to make sure this is fully simplified. This thing is, we want to know 100 minus P equals 0. What's going to make that equal to 0? If I add the P over, that might be the quickest way to solve for it. 100 or P equals 100 is going to be the thing that makes it equal to 0. My vertical asymptote is 100. If I'm looking along here, this is the mark somewhere. So now it is looking at, this is C or cost over here in dollars. And this is removing what we're doing on this line. So what they're saying is we'll never get to this, but as we get closer to this, it's going to shoot off here, right? Okay, so what does that mean? If we're looking at this thing, we can spend an extra, oh man, 250, 500, so that would make 1, 2, 3, 4. Each of those is 50, so these little lines is 50. So going between like what, 20 and 30%, we're spending 50, between going like 30 and 40, we're going to spend 75. So each amount more that we go, right, it's going to cost us like exponentially more almost to get this thing, to remove more and more pollutants. So one thing is that you're never going to reach 100, right? That's one thing. It's an acid. You'll never reach 100%. You get probably like 99.999, but there's never going to be 100% clean smokestack. After you burn something, there's some sort of pollutant there. There's no such thing as clean coal, right? Is what this is telling me. The other thing is that you'll spend more and more for less and less, right? For less results. Like to remove 10% here might be the same cost as removing like 1% over here, right? Or even 0.1 as we get closer and closer. And so at some point, you have to ask yourself, how much of this do I need to remove and how much it's going to sort of cost me, right? Okay, so that is the final word problem for the section. I will see you all soon in class. Study hard and take care.